Hello, I welcome you all to this class. Now we are going to solve one numerical problem which is based on the Brayton cycle, right? So the problem is on the screen that air enters the compressor of a gas turbine plant operating on air standard cycle at 100 kilopascal and 300 Kelvin with a volumetric flow rate is 5 meter cube per second. The compressor pressure ratio is 10. The turbine inlet temperature is 1400 Kelvin. The turbine efficiency, the turbine and the compressor isentropic efficiency has 80%. Calculate thermal efficiency, the back work ratio and the net power developed in kilowatt. So this is your questions. So first of all, the question is about simple Brayton cycle, that you can say the Brayton cycle is one in which we have a four process. Two are the isentropic compression and expansion, and the heat supplied and heat rejection is at constant pressure. Or also, if you remember, the gas turbine works on the Brayton cycle, right, which is a constant pressure cycle. Okay, so this is the simple or the general Brayton cycle, or you can say that it's a open constant pressure open cycle gas turbine, right? So now first of all, to solve the problem, we would like to draw the temperature versus entropy diagram, and then we'll see then how can we execute the problem. So first we have to draw temperature entropy diagram. So we are drawing the temperature entropy diagram. Let's start. Right, so you have a solution here. Okay, first of all we will draw the temperature and entropy diagram. Yes, so temperature and entropy diagram we are drawing here. This is a simple gas turbine, means the Brayton cycle, right? So this is the temperature on y-axis and the entropy on x-axis, right? Now the two constant pressure line we have to take. Let's say this is the high pressure line and this is your low pressure line, right? So first of all, the two process we have to show, the ideal as well as the actual. So ideal is nothing but the isentropic compression and expansion, and the actual is the reversible adiabatic compression and reversible adiabatic expansion, right? So first I'll showing that this is the ideal process, right? So this is 1 to 2. Okay, then 2 to 3 we have a heat supplied in a combustion chamber, and 3 to 4 it is an isentropic expansion, right? So this whatever the process I have shown here, this is the ideal process, means these are the isentropic compression 1 to 2. Okay, so it is isentropic compression, heat supplied at constant pressure in combustion chamber from 2 to 3, and this is the isentropic expansion in a turbine, and further you are rejecting the heat from 4 to 1. All right, now next we have to show that is actual process, right? So for actual, how it is that this you can see, this is your actual, that is 1 to 2 dash. This we call it as a reversible adiabatic compression, and 3 to 4 dash, this is the reversible adiabatic expansion. All right, now so first of all, if you see, the question is air enters the compressor of a gas turbine plant operating on air standard cycle at 100 kilopascal, right? So air enters the compressor of a gas turbine plant. This is the compressor, this is the inlet of the compressor, exit of the compressor, inlet of the turbine, exit of the turbine, right? So now air enters the compressor plant operating on air standard cycle has 100 kilopascal and 300 Kelvin, means the pressure and temperature at the time of entering into the compressor is 100 kilopascal and 300 kilopascal. So first you can write on the given data that given data we have P1 is equal to 100 kilopascal, right? and the T1 is equal to 300 Kelvin, right? Further, with the volumetric flow rate. Volumetric flow rate means what? The volume flow rate is given V dot, right? V is the volume and flow rate is for the it is given 5 meter cube per second. Means in 1 second 5 meter cube of air is entering, right? The compressor pressure ratio is 10. So the compressor pressure ratio, you can say here that compressor pressure ratio means what? That is Rp is equal to 10, right? So for better understanding, you can write here that Rp is equal to what? P2 by P1, right? Compression pressure ratio, this is only, right? Then the turbine inlet temperature is 1400. So you can see, as I told you, this is the inlet of the compressor, exit of the compressor, inlet of the turbine. So the turbine inlet temperature is 1400 Kelvin, or the entrance temperature at the turbine will always throughout the cycle. So this is the maximum cycle temperature also, right? So whenever it is mentioned that maximum cycle temperature in the cycle, it means that it is the turbine inlet temperature only, right? So the turbine inlet temperature is 1400, which is nothing but the T3. So T3 is how much? 1400 Kelvin. Alright, as well as the efficiency of compressor and the turbine efficiency is given. So both the efficiency is same. It is given in the question that compressor efficiency neta C is equal to neta T. That is, neta C is nothing but compressor efficiency and neta T is the turbine efficiency, which is the 80%, right? Then that the fluid which is enter into the compressor, it is the air, right? So air properties we will take. That means what? The specific heat at constant pressure of air is 1.005 kilojoule per kg Kelvin, and the adiabatic constant, which is gamma, will take it as a 1.4. So you can additionally write, that is not given in the question. So you need to remember that for air, right, specific is constant specific heat at constant pressure is 1.005 kilojoule per kg Kelvin, right? And the adiabatic constant, that gamma, is equal to 1.4, right? And if the gas constant is also, you can write that R is equal to 0.287 kilojoule per kg Kelvin. This data you should remember right now. So this is what we have we have written the given data. Okay, now if you look at the TS diagram, right? If you look at the TS diagram, so 1 to 2, 3 to 4 is the compression and expansion. So you have only the data is given, P1 is given, right? That is, P1 is given, T1 is given, T3 is given, right now, and the pressure ratio is given, which is 10, and as well as the compressor efficiency 80% and the turbine efficiency is also 80% is given. It means we don't have T2 dash, T4, T4 dash, T2, right? So this data is not given. First, what you have to calculate, the thermal efficiency you need to calculate. So thermal efficiency is what? The thermal efficiency is nothing but net work by heat supplied. So for that, for finding the net work, you need to find out the turbine work and the compressor work. That actual turbine work and actual compressor work means the work which is executed in reversible adiabatic compression and expansion, and the heat supplied is what? 3 to 2. So for that we need to know the T2 dash and T4 dash, right? So how can we calculate? We'll do that. So first of all, just hold on. Yes. So first of all, you can write from 1 to 2 process, right? 1 to 2 process. Okay, 1 to 2 process. So 1 to 2 process, first I'll take the that is isentropic, that T2 by P1 is equal to P2 by P1 whole power gamma minus 1 by gamma. This you know from the thermodynamics, that temperature pressure relation, right? Here just for we can say Rp is equal to P2 by P1, which is given, right? So now we need to find out the T2. So T2 is equal to what? Directly I am writing that T1 times of Rp whole power gamma minus 1 by gamma. Just cross multiply, put the values. T2 is equal to T1 is how much? 300, and Rp is 10. Right, so 10 gamma we have taken for the air is 1.4, so 1.4 minus 1 is 0.4 upon 1.4. So your T2 value will get, right, so this is the 579.2 Kelvin. Okay, so first temperature we got at the end of the compression, right? This is the ideal temperature, right, which is we are getting after compression isentropically. Right, now we'll get the actual temperature, means when the compression takes place, reversible adiabatic, that is 1 to 2 dash. Right, so for 1 to 2 dash we need to use the compressor efficiency. So you know the compressor efficiency is what? That neta C is equal to isentropic work right, by actual work. Right, now by actual work. So work is what? That work is nothing but you can say MCP T2 minus T2 minus T1 for isentropic, and actual is MCP T2 dash minus T1. So MCP CP will get cancelled. So you can write here that isentropic work means what? T2 minus T1 by T2 dash minus T1. Okay, so from here you can get that answer, that compressor efficiency is how much? That is 80%. 80% means 0.8 is equal to T2 we have. Okay, so this is 579.2 minus T1 is 300 upon T2 dash we have to calculate, that is actual temperature at the end of the compression, minus 300. Okay, cross multiply, so this will be 0.8 into T2 dash minus 300 is equal to 579.2 minus 300. Right, so the equation will become like this, that when you simplify this efficiency will come to the denominator and T2 300 will be added. So here you can write T2 dash is equal to 579.2 minus 300, that 0.8 will come in the denominator, that 0.8 plus 300. Okay, so this you just for understanding, I'll show you that how it came. So while you calculate, you'll get the values at 649 Kelvin. So actual temperature at the end of the compression that we got, this is the T2 dash is 649 Kelvin. Right, now, so it means that at the end of the compression temperature we got. Now what we need to do, we need to find out the temperature at the end of the expansion. Right, why? Because at the beginning of the expansion the temperature is given, but we don't have a temperature at the end of the expansion. Right, so for that you can see here the expansion is taking place from 3 to 4. That 3 to 4 is the isentropic expansion in a turbine, and 3 to 4 is the reversible adiabatic expansion in a turbine. Means you need to find out the ideal temperature as well as the actual temperature. So first of all, for 3 to 4 we'll use the temperature pressure relation, and for 3 to 4 dash we'll use the turbine efficiency equation. So let's do that. So here you can write that 3 to 4 process. Okay, 3 to 4 process. So same equation we need to write that T3 by T4 is equal to P3 by P4 to the power gamma minus 1 by gamma. So first you can write T3 by T4 is equal to P3 by P4 whole power gamma minus 1 by gamma. But you know that P3 is equal to P2 and P4 is equal to P1. It means that from this relation. Why? Because the P3, 2 and 3 is a constant pressure line, and 4 and 1 is also constant pressure line, right? Means heat supplied at constant pressure and heat rejection at constant pressure. That's why these are equal. So when you see this, P3 will become P2 and P4 is become P1, which is nothing but the Rp, right? And the Rp value is given, which is 10. So directly we can say we need to find out the T4. So T4 is equal to T3 by Rp to the power of gamma minus 1 by gamma. Okay, actually you cross multiply and then that Rp will goes to the denominator. Now you can say T4 is equal to T3 is given, which is 1400 Kelvin, right? So 1400 Kelvin by Rp is what? 10, and the adiabatic constant is 1.4. 1.4 minus 1 is 0.4 by 1.4. So this is 0.4 by 1.4. So T4 we got, right? So after calculation we'll get the temperature at the end of the expansion, that is the isentropic temperature at the end of the expansion is 725.12 Kelvin. As I told you that when whatever the calculation I am doing here, so you need to re-verify, right? So it may be that there is a human error right now. So at temperature at the end of the expansion we got, which is the sorry, this is not the T4 dash, this is the T4, right? So T 725.12 Kelvin. Now we need to find out the temperature at the end of the reversible adiabatic expansion, or you can say the temperature at the actual temperature at the end of the expansion we have to find, right? So for finding the actual temperature at the end of the expansion, we will use the turbine efficiency, right? So you know the turbine efficiency is what? That neta T is equal to, this is the actual by isentropic work, right? So you can say the actual work, turbine efficiency is actual work over isentropic work, right? By isentropic work. So work is in terms of the MCP, T3 minus T4 dash by T3 minus T4, or you can say the H3 minus H4 dash by H3 minus H4, and H is a function of temperature right now. So that you know in your basics of thermodynamics. So you can say here that is T3 minus T4 dash by T3 minus T4. All right. Now you need to cross multiply and get the T4 dash value. So directly I am writing, see when you cross multiply this, so T3 minus T4 into NT will become, or you can see here NT into T3 minus T4 is equal to T3 minus T4 dash. Okay, now we need to find out the actual temperature T4 dash. So what you can do, that T4 dash is equal to T3 minus, this whole will come to this side, minus turbine efficiency into T3 minus T4. Alright, so this is T4 dash is equal to T3, you have that 1400 Kelvin at the entrance of the turbine. Turbine efficiency is given 80%, which means 0.8. T3 is further at 1400 minus T4 you got just now, which is your 725.12, right? 725.12. So while you calculate this, so after calculation means after simplification, you will get the actual temperature of the turbine at the end of the expansion, which is 860 Kelvin. So I think so now we got all the temperature at the compression and expansion of the TS diagram, right? So first of all we need to find out the thermal efficiency. So for finding the thermal efficiency, you know that net work by heat supplied. So first we'll calculate the turbine work, compressor work and the heat supplied, right? So first of all we are finding the actual turbine work. We don't use the isentropic work file while finding the efficiency of the plant, right? So you can say the actual turbine work, right? So where the turbine is working, if you see that the turbine is this, so T3 minus T4 dash, and the actual compressor work is T2 dash minus T1. All right, now just hold it. So you can say that actual turbine work is means that WT is equal to what? Cp into T3 minus T4 dash, right? Or you have a, in terms of the enthalpy, it will become H3 minus H4 dash, right? Now, so Cp is what? The specific heat of air is 1.005. T3 we got, T3 is given in the question itself, that is 1400, and T4 dash we got just now, which is 860 Kelvin, right? So while you calculate this, you will get the values. So turbine work is 543.7 kilojoule per kg, right? So you need to cross verify this answer whether it is that formula substitution and everything is correct, right? Maybe the numerical data can be mistake. There is little chances, that 0.1% I am telling, but for the satisfaction you need to re-verify. Then turbine work we calculated. Now we need to find out the actual compressor work, right? So we can write here that actual compressor work. So actual compressor work means the WC, we can say WC is equal to, further Cp, T3 minus T4 is for the turbine, so it is what? T2 dash minus T1. So you can say the Cp T2 dash minus T1, or in terms of the enthalpy it will be H2 dash minus H1. So you know that Cp is 1.005, T2 dash is what? T2 dash you can see where we got, yes, 649 Kelvin, right? So this is your 649, and T1 is given, which is 300. So after on calculation we'll get the compressor work, that is WC is equal to 350.745 kilojoule per kg, right? So this is what we calculated our compressor work also. So now we have a turbine work, we have a compressor work. You can find the net work also right now. So here only you can write, just that is net work. That's better. So just a sec. So this is what you have, a net work, right? So net work is what? That W net is equal to turbine work minus compressor work. Why? Because in gas turbine plant we know that the compressor is a work in, means we have to give the work to the compressor, right? And turbine is the power output. So first of all the work we are supplying to the compressor, and then the remaining work is responsible for the power generation, right? So it means that whenever you have to find out the efficiency of the plant, means you need to subtract the work from the compressor, right? Then the turbine work is how much you got? 543.7 minus the compressor work is here 350. This is minus 350.745. Okay, so on calculation we'll get the values as 192.95. This is your kilojoule per kg, right? And this is the net work, that W net we got. So this is your W net, that is net work. Now we need to find out one more data, that is heat supplied, and then we'll substitute the answer, right? So here, just wait. So now you can say the heat supplied. The heat supplied in a combustion chamber, right? So heat supplied is what? That either you can write HS or Q suffix S is the Cp from where to where? T3 minus T2 dash, right? So Cp is what? 1.005, and T3 is given 1400 Kelvin. Actual temperature at the end of the compression you got, which is 649, right? Now T40 649. So on calculation you can get the heat supplied is, wait, we'll do the calculation, 1.005, and the temperature is 1400 minus 649. Okay, so the heat supplied is this 754.755, right? So this is the 754.755 kilojoule per kg. This much of heat you are supplying. Yes, 754. So now that heat supplied is this one, then first bit we can write the thermal efficiency, right? That is the thermal efficiency. Okay, thermal efficiency. So neta TH is equal to what? Neta TH is equal to W net by heat supplied. So W net is what? W net you have calculated, which is your 192.95 upon heat supplied is 754.755, right? In 200 you have to do to get the percentage, which is actually it will come in 0.255, right? So when you multiply it with 100, it become 25.56%, right? So the thermal efficiency of a cycle, you can see how much, that is near about 26%, which is exact values is 25.56%, right? Okay, next we have to find out the back work ratio, right? The second big bit we have to find that, which is the back work ratio. So back work ratio is what? The back work ratio is nothing but the net work by turbine work, right? So we can say here that second we have to find back work ratio, right? Back work ratio. So back work ratio is what? We can write in short, BWR is equal to W net by turbine work, right? So W net is how much? W net you got already, which is 192.95, and the turbine work is 543.7. So this will come 0.646, right? Which is nothing but the 64.6%, right? So this back work we also get. Next we have to find out the power output of the plant. So see that power is nothing but the turbine work, right? So that is net work. So whatever the net work we calculate, if you multiply that net work with the mass flow rate, we'll get the power. So in the question the mass flow rate is not given, don't be confused. This is the what the trick they have given right now. So you'll get confused that volume flow rate is given. So from the volume flow rate we'll get the mass flow rate, right? So you can see here that first of all, third bit they are asking that find out the power output of the plant. So power output of plant, right? So power output of plant we need to find first. So for that we need to know the density. So density of the air, how can you calculate that? PV is equal to mRT, you know, right? So I'll show you here that PV is equal to mRT, right? So when the volume will come in the denominator, it become rho, that it leads you that P is equal to m by V into RT. That mass by volume is what? Density. So this will become that pressure P is equal to rho, this is pressure and this is rho, density, rho RT, right? So here you can say that density of the air is equal to P by RT, right? So density of the air we got, that is P by RT. P is the pressure and R is the gas constant, T is the temperature. So let's say the density of the air at the entrance, right? So P1, rho 1 is equal to P1 by RT1, right? Now so this is what P1 you have given, which is pressure is entering into the compressor at 100 kilopascal. So this is the 100 kPa, right? By R is 0.287 kilojoule per kg and temperature is 300 Kelvin. So when you substitute, you will get the density of the air which is entering into the compressor is nothing but 1.16 kilogram per meter cube, right? So this is how we calculated the density of the air. This is 1.16 kilogram per meter cube. Now from that continuity equation, that mass flow rate will calculate, and when you multiply that mass flow rate with the net work, you will get the power. Okay, so here you can see that first you have to find out the mass flow rate. Okay, mass flow rate is what? That m dot a is equal to density into volume flow rate. Okay, so this is m dot a is equal to density is what? 1.16, just now we have calculated, and volume flow rate is given in the question 5 meter cube per second. So this will become 5.8 kilogram per second. Then whenever you multiply the mass with the net work, you will get the power, you know. So power develop is what? That power output of the plant is equal to mass flow rate into net work, right, into W net, right? So mass flow rate is what? 5.8, and the W net we have calculated, which is 192.95 kilojoule per kg. So this answer will come in kilojoule per second, which is nothing but the kilowatt. So this is 2.73 kilowatt. This is your power output of the cycle, right? So this is how we can simplify the problems, right? So in the next video we will solve some more problem. The problem will be related to the intercooling, reheating and regeneration. So for latest update, please like, subscribe, comment and share with your friends. Thank you.